Okay, hello everyone. The purpose of this video is to go over a lot of the example problems that we didn't have time for today in lecture. So the first one of these is maybe not so much an example as a proof. Um, so we want to derive an equation. So maybe I'll tell you the setup, I'll give you the answer, and then we'll go over the proof. So if you have a projectile that's launched from the ground or any height, and it has some initial speed v naught. So that's the total initial speed. It has a smaller x component and y component. So initial speed v naught, it's launched at some angle relative to the horizontal theta. Um, so that's actually all that's given in the original problem. And so what it's going to look like is it's going to be parabolic. That's a bad parabola. The parabola is symmetric, so it's supposed to look like, that's a little better. Okay. And suppose we wanted to solve for the range, which is the total horizontal distance covered. Range R equals what? So the convention is that if a figure has a variable labeled, then a lot of times that's what you're given in the problem. So like the fact that we labeled V naught and theta signifies that you're given that info. So your final answer can involve those quantities. But you're not given R. That's actually what we're solving for. And very explicitly, we're saying equals what? Equals, we don't know from the very beginning. And the stipulation here is that the final height has to be the same as the initial height. So this formula won't work if it landed, up here or something on some hill, or if it went downhill anymore. So the final moment has to be at the same elevation. So this is so y final equals y initial is important for this. Um, So I said I would give the answer, but let's just go ahead and solve and prove this. It's not so bad. Um, okay, as we've gotten some practice already, we definitely want to split up what's going on in the x direction and the y direction. So the x component of the velocity, which is going to remain constant throughout the whole motion, is going to be v naught cosine theta. And so the range, so delta x is what we're calling range for this particular problem. And that's just going to be Vx times time. So the range is Vx is V naught cosine theta times time. So we would be done. This would be our answer because we're allowed to use V naught in our answer. So this is a known because we want our final answer in terms of V naught. We're allowed to use theta in our answer, but we're not allowed to use time in our answer. So we're going to have to plug in something for time. We have to find the time in terms of V naught and theta. So we're kind of stuck at this point when it comes to just the x directions. So now we have to look at the y directions. So the goal is to write the time in terms of things we know, and then we're going to plug it into here. So we want to use this. We still haven't used this fact yet that the final y position is equal to the initial y position or y elevation. So let's go ahead and enforce that fact. So delta y is 0. So this is v naught y time minus 1/2 g t squared. Right. Okay. So we're going to factor out a t here. So there's going to be two solutions for time for this quadratic formula, or for this quadratic equation for t. But t equals 0 is just the moment it's fired, right? So we're not so interested in that solution. We're really going to be interested in this other solution. So the other one is going to be, we're factoring out a single factor of t. The first term is v naught y. But v naught y is v naught sine theta, similar to this right here. So this is equal to this, and this is equal to this. And this all comes from, taking this initial velocity vector and decomposing it into Vx, V naught x, and V naught y. Okay, so if you wrote down sine theta equals opposite over hypotenuse, this is easier to see maybe. So sine theta is opposite over hypotenuse. And then if you rearrange that and solve it for v naught y, you get v naught sine theta. And then minus 1/2 gt, right? We factored out a t. So if you're wondering where the t squared went, there's one t outside and then one t inside here. So the solutions here are t equals 0 or t equals 2 v naught sine theta over g. Which is good because we know what v naught is, we know what theta is, and we're allowed to use, and g is just a fundamental constant. It's always 9.8 meters per second squared. So we know what time is at this point. So now we can just take this value for t and plug it in right here. And this will finish up our derivation, our proof. So going back to like the work that's in the black pen here. So the range is v naught cosine theta times time. So time is 2 v naught sine theta over g. So you can write this answer a couple different ways. So one way is v naught squared times 2 sine theta cosine theta over g. And we could be done. But there is a trig identity that says 2 cosine theta sine theta is sine of 2 theta. So this is most often represented this way. R is equal to this formula right here. So this is called the range equation. Derivation. For some reason, it became French or something. I guess if it was Spanish, it would be derivation. So the interesting thing, I mean, what's something to keep in mind here is that it becomes clear with this formula that the maximum range for a given speed, for a given v naught, so say v naught is constant and then g is constant. Imagine you're allowed to change the angle of the projectile. The maximum value that sine of something can have is 1, and that happens when the argument is 90 degrees. So the maximum range happens when 2 theta is 90 degrees, or when theta is 45 degrees. So in the absence of air resistance, you want to launch a projectile at 45 degrees to maximize how far it will go in the horizontal direction. Okay, let's continue with the next example. A ball is thrown from a cliff. So I immediately want to draw a picture to symbolize this. And by the way, on the so the idea for the original slides was that we would solve this just in terms of abstract parameters here, v naught and h. And so we would have an answer in terms of v naught and h. But given that we're solving a quadratic equation here, this can get pretty cumbersome. So we're actually just going to go ahead and plug in numbers here. So forget the v naught. We're just going to plug in the speed. Initial speed is 10 meters per second at an angle 30 degrees above the horizontal. So what that means is, so the speed is 30 meters per second, and the angle is relative to the horizontal. So the horizontal, no matter what height you're at, is just the horizontal line. So this angle right here is going to be 30 degrees. Oh, sorry, I said 30 meters per second, but this is 10 meters per second. And the cliff has height 30 meters right here. 30 meters. So the motion of this is going to look like this, and we want to know how far from the base of the cliff this is. I'm going to call this, well, we'll just call delta x. I don't want to call it r, the range, because we can't use this formula. So I'm not quite going to call it range. Remember that we had to have that the final elevation was equal to the initial elevation in order to use this formula. So if that's not true, like for this problem, you can't use that equation. Yeah, it's not relevant here. So let's see, we want to solve for delta x. The x equations are pretty straightforward, right? It's Vx times time, and Vx is going to be 10 meters per second times cosine of 30 degrees times time. So at this point, we could plug in 10 meters per second and cosine 30 degrees, but we don't know time. So again, not again in the video, but again in that I mentioned this in lecture. The only variable that's common to the horizontal and the vertical directions is time. So so we're kind of stuck in the x direction, but in order to solve for time, we can look at the y direction. All right, so it looks like, so we want to solve for time. We don't care about the final velocity, and we don't have the final velocity y component. So that's a big sign that we're going to use this equation right here. Delta y is v naught y time minus 1/2 g t squared. Delta y is going to be negative 30 meters, right? The final is below the initial. So final minus initial is going to be negative. So negative, overall, the displacement in the y direction is negative 30 meters. V naught is 10 meters per second times time. Sorry, it's 10 is the V naught, but we want V naught sine theta, so sine 30 degrees times time minus 1/2. And since we're starting to plug in numbers, we can go ahead and plug in 9.8 meters per second squared t squared here. Now this is where it gets interesting. So this when I look at this equation, I get a little uncomfortable because I have units right here. These are units, but this right here is an actual variable. Right? And it looks a little confusing, right? Because there's a lot of letters running around. There's M, S, and T. But really the M and the meters and the seconds are just units that come along for the ride. And I don't really want to, I want to emphasize that this is actually just a quadratic equation. So I'm just going to say, at this point, I'm going to assume SI units. So a lot of you just do this automatically. I'm trying to be careful about it. So at least I'm going to tell the reader, like, look, we're going to assume SI units everywhere. And then the answer is going to spit out in SI units. So we have this equation, minus 30 is 10 sine 30 degrees. So sine 30 degrees is 1/2. And then 10 times 10 is 5. So it's 5t. We're also being a little sloppy with the sig figs here. So I'm probably just going to give an answer to 2 or 3 sig figs, just as conventional for physics classes right now. And then minus half of 9.8 is 4.9 t squared. Right. So if you move the 30 over to the other side, maybe just make this, playing with colors at this point, 0 and then plus 30. So now this is just a quadratic equation. You have at squared plus bt plus c equals 0. And we're going to solve for t. Now you can anticipate, like, are both solutions for time going to be positive? Are both going to be negative? Or is there going to be one positive and one negative? So before I even solve this quadratic equation, I want to look at this diagram. And I'm going to go ahead and plug in that this is the moment t equals 0. T equals 0 is right there. And when the projectile is moving, at any point over here, this would be positive time. So basically right here, this is t greater than 0. And really, the projectile, the formulas for the quadratic equation here are not really relevant because you threw it at t equals 0. At negative time, the rock wasn't, down here. It wasn't flying up along this parabola, right? But if you continue the motion in the negative direction, it would be. So there is going to be really, if you extrapolate this backwards, there is going to be a negative time solution to where delta y was negative 30 degrees or 30 meters, right? So it's just at what time values is the projectile at this height right here? So it looks like there's going to be one negative solution and one positive solution, but we're going to ignore the negative solution given the problem setup. Okay, so we definitely want the positive time here. So I'm going to go ahead and plug in this formula into my quadratic equation solver on my computer. You can use Wolfram Alpha. I'm basically using Wolfram Alpha for this. And solve 0 is 5t minus 4.9 t squared plus 30. Solve for t. And as expected, we got a negative solution and a positive solution. So t equals negative 2.0 seconds So at this point, I'm going back in and plugging in the SI unit for time, which is seconds. Or t equals 3.036 seconds. So I'll just say t equals 3.0. So the final answer I anticipate, I want to do 2 sig figs. Whatever final answer you have, you probably want to keep 1 more sig fig in the intermediate steps. So actually, right here, I'm going to write down 2.02 seconds, or t equals 3.04 seconds. And this is the one we want to focus on. This is the one we need. So this is the one we're going to plug in here. So it looks like delta x is equal to 10 meters per second times cosine of 30 degrees. Make sure your calculator is in degrees, or you convert that to radians. And the time is 3.04 seconds. It looks like we get 26 meters right here. Yeah. So it looks like it turns out we would have been safe if we had just kept the 3.0 seconds originally. But sometimes you can have these rounding errors that accumulate. So it's a good idea that whatever you have in mind for the final answer, sig figs, keep 1 more in the intermediate steps, and then at the end, go ahead and do the sig figs that you wanted to do. Okay. So I think that does it for the projectile motion problems examples. There were a couple relative velocity problems that we didn't get to. So there's an example, a clicker question, and then a problem at the end. So let's quickly go over these. There was a typo, by the way, in this example too. So this should say person C instead of person A right there. Okay, a train is traveling to the right at 10 meters per second. So implied in this is relative to the ground or relative to the track, right? It's not saying relative to anything else. So we're used to this being like relative to the stationary Earth, right? So so A will be train A. I want to label these subscripts as I'm going to use them in my velocity. I'm going to be writing things like the velocity of A relative to C, right? So I want a single letter here to symbolize different objects and reference frames. So A is train A, which is both an object and a reference frame, right? You can talk about the velocity of something relative to that train, or you could just talk about the speed of the train or the velocity of the train itself relative to some other reference frame. So A is train A, B is train B. C is a person. C is the one person. It's called person C. And it looks like we also have the ground, right? G is the ground. We have 4 objects here. Okay, so let's write down all the known quantities, the things that were given, and then I'll go ahead and write down what we want to solve for. So the velocity of train A relative to the ground is plus 10 meters per second. So I'm going to just indicate the direction with a plus or a minus sign. So this is going to be the positive direction. Plus x hat or I hat, they mean exactly the same thing. I like x hat. Train B is traveling to the left at 15 meters per second. So the velocity of B relative to the ground or the track is negative 15 meters per second. Person C is walking to the right on train A at 1 meters per second. So the person's walking relative, the person can walk at a certain speed relative to the ground underneath them, but they're on top of train A. So they're walking at 1 meters per second relative to train A. The velocity of person C relative to train A is positive 1 meter per second. And what we're trying to solve for, what we want, is the velocity of person C as observed by a stationary observer on train B. Okay. So you can kind of chain together these velocities as you need in order to get the subscripts appearing in exactly this this combination CB. So VCB is equal to the velocity of C relative to something else. And it looks like what we have here is the velocity c relative to a. So let's start it by this. And then it looks like the way we can connect all of these is we know the train A relative to the ground and then the ground relative to train B. So it looks like the way we want to chain all these together is A relative to the ground and then the velocity of the ground relative to train B. So I'm going to get rid of the velocity sign here. Everything's in 1D, so we can just write these as positive or negative numbers. So VCB, which is what we're trying to solve for, is VCA, which is plus 1 meters per second. And then AG is 10 meters per second positive. I'm just reading these off right here and here. And then GB is, so if we flip the indices here, so G relative to B is opposite B relative to G. Sorry. So it looks like if we have VBG is negative 15, then VGB is plus 15 meters per second. Okay, so I'm going to go ahead and plug that in here. So this is plus 15 meters per second. So then we get VCB is 1, 10, 15 is 26 meters per second to the right. So notice how I didn't write my answer as I hat or X hat because nowhere in the problem statement did they introduce a coordinate system. It was to make my life easier that I introduced plus X. So my answer is a positive X component, but you know, in terms of the description of whoever wrote the problem, they just use left and right. So it's preferable to translate your answer into a form that the person who wrote the question would understand, right? Left or right. So vector, v vector, magnitude and direction. Magnitude is 26 meters per second, directions to the right. Okay, so we did this question in lecture, which was rough, obviously. But even if you're confused now you know how to do it. So let's make sure. Okay, so we introduced the 4 objects last time. So we had the North Pole, we had the bear, we had the water, and we had the fish. And this question, oh, current or water? I guess I called this water. Whatever. You could label this one C. Same thing. Okay, what is the velocity of the fish relative to the North Pole? Well, we know the velocity of the fish relative to the water. That was given. And then we also know the velocity of the water relative to the North Pole. And notice how I wrote the indices so that these two would, when you sandwich it together, you're just left with Fn. Oh, sorry, I'm labeling P for pole and N for North Pole, but they're the same thing. Okay, so so I'm gonna go ahead and write this without the vector signs. So the fish relative to the water is going in the negative x direction. So this is the positive direction. The velocity of the fish relative to the water is, looks like negative 10. Right? The fish is swimming at speed 10 in the negative direction. So this is negative 10 meters per second for fish relative to water. And then the water relative to the North Pole, it's drifting away at 1 meter per second. So it looks like the fish relative to the North Pole is negative 9 meters per second, where the speed is 9 meters per second. Okay. Last question. Okay, a truck is traveling south at a speed of 70 kilometers per hour towards an intersection. Car is traveling east towards the intersection at a speed of 80 kilometers per hour. What's the velocity of the car relative to the truck? So it looks like they already labeled in the problem statement, they give us the labels that we should use. It looks like there's C for car, T for truck, and E for earth. And so what we want to solve for velocity of the car relative to the truck. So the strategy here is to write down, this is going to be the sum of two different velocities. And we want to choose the indices so that we're going to choose something in here so that that index is going to cancel, right? It's the velocity of the car relative to something, and then the velocity of that something relative to the truck. And when we add those two vectors together, we'll get the velocity of the car relative to the truck. And the only other object or frame that's relevant here is the Earth. So we're given VCE is to the right. We're given the velocity of the truck relative to the Earth, which means that the velocity of the Earth relative to the truck is in the opposite direction, but also at 70 kilometers per hour. So what this equation is saying in pictures is if I take the velocity of the car relative to the Earth, and I add together the velocity of the Earth relative to the truck, then the sum here is going to be the velocity of the car relative to the truck. So it looks like it's going to point up and to the right. Okay. And so there's a velocity vector here, so we need to give magnitude and direction here. So let me carve out some room. Let's just go ahead and write this in terms of components, so I hat and j hat. So the velocity of the car relative to the truck looks like VCE is 80 kilometers per hour in the I hat direction. And then this one is going to have a positive y component. So plus the velocity of the Earth relative to the truck is plus 70 kilometers per hour in the j hat direction. So this is our answer right here. Now we could find the magnitude of this by do square root of 80 squared plus 70 squared. That would be the speed in kilometers per hour. And then the direction, we could solve for this angle, knowing that this is, it's like 80, 70. So it's going to be an angle that's a little less than 45 degrees, right? If they were the same number, it would be exactly 45 degrees. But you go a little bit more in the horizontal than vertical, so the angle is a little smaller. I wanted to quickly delete it because I didn't write down the units, and that's sloppy. I didn't want to do that. So I got those out of there. Okay, I hope these examples made sense and were helpful.